the screen.
Yes, sir.
So in the previous class, we were doing this VBT, right? In which I told you that if a strong field ligand will be there, then that means pairing will take place. And if weak field ligand is there, then pairing will not take place. And you have done some questions on this, right?
Yes, sir.
Now I'm going to give you another question for this, in which I will tell you which one is strong and which one is basically the ligands that is present in this compound is this is basically a strong field ligand. So for this compound, you need to calculate the hybridization, then tell me about the geometry, as well as then tell me about the magnetic nature, and then you are going to tell me magnetic moment. Please solve all this.
Okay, sir.
Do let me know when you are done with this. And let me know if you are facing any kind of problem. A strong field ligand, that means pairing will take place.
So the oxidation is +3.
Yeah, that's right. Its oxidation state is plus.
So the hybridization is D2sp3.
That's good. It's due to sp3. Then geometry will be octahedral, right?
Yes, sir.
Can you tell me about the magnetic nature,
So it's
whether it is
diamagnetic.
paramagnetic or diamagnetic? It is diamagnetic because all are paired. Very
Yes.
good. What about the magnetic moment? Mu,
So it will be
that will
zero.
be 0. So this is the concept for your VBT. I think it's clear, right? Now moving to the next, that is crystal field theory. And we also call it CFT, crystal field theory. Now see, I'm going to write some points about this. So write with me. CFT, that is crystal field theory, is an electrostatic model which describes the electronic structure of metal ions in ionic ligands. Of metal ions in ionic ligands. Next point we can write. Just write with me, then I will explain. It provides an approximate distribution of energy level. Distribution of energy levels which determines the ultraviolet and visible spectrum. The ultraviolet and visible spectrum, but not the bond. It doesn't say anything about the bonding much. In free state, which is very important, in free state, or you can say isolated alone, it is when it is alone. All the d orbitals, we have 5 orbitals, all the d orbitals, d subshell has 5 orbitals, that is your dxy, dyz, dxz, dx square minus y square, and the fifth one is dz square have same energy, called degenerate orbitals. That means basically what I want to tell you is that when all the orbitals of d will have same energy, then they are known as degenerate orbitals, and when d orbitals are in free state or isolated state, they will be degenerate orbitals. Is that clear?
Yes, sir.
So please do write this. Are you done with this?
Yes, sir.
Okay. Now we are going to draw some structure of this dxy. So do you know the structure of these orbitals? This is x and this is y, and you want to draw the structure of the xy orbitals. This will be in between this xy. Are you getting my point? If you are going to draw the structure of dyx, dxz, let's say this is x and this is z. So the structure of dxz is like this. There will be like this. And if you are going to draw, this is y, this is your z. So this is the structure of dyz. dxy, dxz, and this is your dyz. Is that clear? Now, if you're going to draw the structure for dx square, this is x, this is y, and if you want to draw the structure for dx square, y square, so the structure, the lobes on the axis, in all of these three that I have written on top, is the lobe is on the between the axis, but in this dx it will be on the axis. Then comes this is your z, and if you are going to draw the structure of dz square, it will be like this. Okay. On the basis of lobes, if you will see, these all four are similar because they have four lobes and it has two lobes. But on the basis of lobes on the axis or between the axis, these are similar because they have lobes on the axis, and these are the lobes which is between the axis. Is that clear?
Okay.
Please do it. Are you done with this, Aman?
Yes, sir.
Okay. Now see, when there is a topic which is very important on the basis of orientation of d orbitals, on the basis of orientation of d orbitals with coordinate axis, they are grouped into two sets. And this is for basically octahedral. The first is basically easy orbitals. And we call it doubly or axial orbitals. And this is basically, these are the orbitals I'm going to tell you. Easy orbital is, since they are axial on the axis, these are dx square minus y square and dz square. Since they are, its name is doubly also because two of the orbitals will be here as they lie on the axis. As they lie along axis. And for the B, you can see T2G orbitals. And you can see here it is triply or non-axial orbitals. And here these are which lie on between axes. So these are triply, that means all the three orbitals which are left, dxy, dyz, dxz orbitals as they lie between axes. So please do write it. After this, I will tell you what is this T2Z and what is this easy and what is its uses. Are you done with this?
No, sir.
Okay, please do it. Let me know when you are done with this.
Yes, I finished.
Now see, write some point about this not the point. Okay, write the postulates of CF. Crystal field theory. Here, anionic ligands are treated as negative point charge, and neutral ligands as point dipoles. You have studied this dipole?
Yes, sir.
Next, according to this CFE, the interaction between central metal atom and ligand is purely electrostatic. According to CF, and there is no mixing. Of orbitals. It is purely electrostatic according to CFE, but according to VVT, it is basically coordinate point. But still, it is not clear that how we should treat, but we study still as research is going on. Okay.
Okay, sir.
So please do write it and then let me know. Let me know when you are done with this.
Yes, sir.
Okay, wait a minute. How is your preparation going?
It's going well, sir.
It's going well. Very good.
Sir, should I
Yes,
practice the sample papers more or the textbook questions, NCRT?
Actually, you should at least attempt a sample paper on a daily basis from now on. Are you getting
Okay,
my
sir.
point?
Yes, sir.
You can go for one sample paper, not for every subject, but yeah, which subject is weaker, like want to today you should, on Tuesday you should solve a sample paper of chemistry. On Wednesday you should separately solve a sample paper of physics. I think it's holiday going on, right? Yes or no?
No, sir. I have my pre-boards next week.
Have you pre-boards?
Yes, sir.
As much hard work as you can do. Okay. But sample paper is also very important, and I have sent 2 sample paper in the group, right?
Sir, not in the group.
No, I sent it. Are
But
you in
I'm
the
not
group?
there, sir. No, sir, I'm not in the group. Chemistry group, I'm not there.
You're not there. Let me tell them to send you. Okay.
Okay, sir. Thank you.
Why are you not in the group?
Sir, they never added me.
Okay. Oh, they never added you. It's not like that. Yeah. I will tell them to add you. Okay.
Okay, sir. Thank
Now,
you.
this is basically d orbital splitting. When d orbital is alone isolated, its energy will be equal, and it is known as degenerate orbitals. And when it is about to bonding, then there will be a splitting of d orbitals into 2 parts, that is T2z and EZ. So basically, d orbital is splitting in an octahedral crystal field. Octahedral crystal field. Now see, this is your d orbitals. Wait a minute. This is your d orbitals. 1, 2, 3, 4. Just write the topic first, and you will get to know what I want to say. So this is your, just suppose this is your dxy, this is your yz, this is your dxz, then comes dx square minus y square, and then comes dz square, right? Now see, this is isolated, so all the d orbitals will have same energy. They are degenerate orbitals. Now, when they are about to bond, what will happen? You will see when they are about to do bonding. What will happen here? 1, 2, 3, 4. There will be a splitting of this d orbital in 2 parts. There will be a splitting of orbital in 2 parts. One is, as you can see, this is your first, and this is your second. And this is known as basically this is known as easy orbital, which is doubly, and this is basically T2G. This is T2G that I wrote triply. Yes or no? Please do let me know.
Yes,
Are you
sir.
getting my point? Now see, this point, what I want to say is that this point is your barycenter. This point is your barycenter. Barycenter. That means basically above this is higher energy and this is lower energy, and also its energy difference is given. This is basically 3/5 delta naught. Delta naught is basically crystal field stabilization energy. Crystal field stabilization energy of octahedral. O for octahedral. A delta naught is crystal field stabilization energy, and this is 2/5 delta naught. Okay, and you can see this is the w dx square minus y square, and this is dz square, and this is dxy, dy, z, and this is dxz. Is that clear?
Yes, sir.
See what happens when it is isolated, they will have same energy. When it is about to bond, so they will have the orbitals will have higher energy than this, and when it will about to bond, then the d orbitals will split into two parts for octahedral complexes. It split it into EZ and T2Z. Are you getting my point?
Yes, sir.
And T2G, you can see this is higher energy and this is low energy. And if you are going to do the electronic configuration will be on the same concept that we did from class 11th. Like the lower energy level will be filled first, then we will go for upper energy level. Are you getting my point?
Yes, sir.
And also, if there will be a strong field ligand, then pairing will take place. I will explain this later. First, right. After this chapter, we are going to start the amines. Okay.
Okay, sir.
Let me know when you are done with this.
Yes, sir. Done.
Very good. Now see, if you have you had CON3 whole 6 raised to the power plus 3, that I gave you this compound for in VVD to calculate hybridization, then geometry, then a magnetic nature, and then magnetic moment, right? So you told me the oxidation state of cobalt is CO plus 3, right? So if you are going to do the electronic configuration, it will be argon 4s0 3d 6. Yes or no? I mean, this is the electronic configuration, yes or no? Please do respond.
Yes, sir.
Now see, this is a strong field ligand. So if you are going to distribute the 6 electron. How you are going to do? First, you are going to do in the lower energy level 1, 2, 3. Where will be the fourth electron going? In this or this? What do you think? The fourth electron.
Send the
Yeah.
top part.
No. Since this is your strong field ligand, so what I told you, pairing will take place, yes or no?
Yes, sir.
So pairing 4, then 5, then 6. If you have another electron, then you will go to this. Are you getting my point? If a strong field ligand is there, are you getting my point? Yes or no?
Yes, I am.
Again, in the previous class, we did for this hybridization and all that, and you calculated CO plus 3 again, and you can see the the electronic configuration is again same. Yes. Now see what will happen. Now, if you are going to do the electronic configuration, since it is weak field ligand, so pairing will not take place. 1, 2, 3, then 4, then 5, then 6. Are you getting my point? Because pairing will not take place in weak field ligand due to weak field ligand.
Yes, sir.
So for this, the electronic configuration in terms of EZ and T2Z for this compound, the electronic configuration of CO plus 3, it will be T2G6 EZ0. Yes or no? In the previous one, all the 6 electrons were
Yes,
here.
sir.
So it will be T2G6 E0. But for COF6, CO plus 3, weak field ligand is there. That means it will be T20 EZ, I'm sorry, T2Z4 and EZ2. Are you getting my point?
Yes.
So can I change the slide?
Yes, sir.
Okay. Now there is this electronic configuration. Electronic configuration. So as you can see, this is your number of electron, and this is your SFL. That means a strong field ligand. That means electrons will pair up. Electrons will pair up. And here it is weak field ligand. That means electrons won't pair up. Now see, if you have 1 electron, 2 electron, we will do up to 10. 1, 2, 3, 4, 5, 6, 7. In a strong field ligand, it is very easy, T2G1, because it is the lower energy level, EZ0. In weak field ligand, it will be also same. Yes or no? You have only 1 electron and it will go in lower energy level.
Yes.
Then the T2G2, EZ0. Then again it will be same, T2Z2, EZ0. Then the third electron comes, T2G3, EZ0. And the third electron, T2G3, EZ0. When fourth electron will come, pairing will take place in a strong field ligand, T2G4, EZ0. And here it will be T2G3, EZ1. The pairing will not take place and the 1 electron will go directly in EZ. Are you getting my point? Are you getting my point? Yes or no?
No, sir, I don't understand.
Okay. If you have 4 electrons, okay? If you have 4 electrons, you see what I'm going. If you have 4 electrons, and if you have a strong field ligand, if you have 4 electron, a strong field ligand, then 1 electron, 2 electron, 3 electron. Yes or no?
Yes.
And the fourth electron, since you have a strong field ligand, the fourth electron will not go here because pairing will take place in a strong field ligand. Fourth electron will be here, T2G in T2G. Yes or no?
Yes, sir.
So that's why I wrote here that it becomes T2G4 because the fourth electron will be paired up in this. And in weak field ligand, the pairing will not take place. The fourth electron will go in EZ. Easy is the higher energy level. Are you getting my point? Yes or no? Please do
Yes, sir.
respond.
I understand.
If you got it, please do up to 10. Please do write this electronic configuration. Then I'm going to give you 8, then 9, then 10. Do the
Okay, sir. Sir, how much space does EG have?
Easy is having only 2 orbitals, so it will maximum accommodate with 4 electrons. Total 5d orbitals, maximum electrons, maximum quota of electron is 10, and T2G has 3 orbitals and EZ has 2 orbitals. Got it?
Okay, sir.
You can look at the diagram that you have drawn. Have you? You have drawn in this part, right? So this is your T2G, this part, and this is your EZ.
So after EG, when it gets full, then it will go to
After EZ, let me know. No, first it will go in T2G, not EZ. This is lower energy level now.
yes, sir.
First
But
it will go in this, and then let me show you what you have written for 5 electrons, 5th electrons.
sir, here T2G.
It is for C.
Yes.
Yeah, T2G what?
5.
Yeah, because it is a strong field ligand, so T2G5 is 0. But when you are going to do it, T2G3 and it becomes EG2, right?
Yes, sir.
For the 6th electron, it will be T2G6, EG0, and here T2G4, again it will come down and pairing starts, EG2. Are you getting my point?
Okay, sir.
Are you getting my point or not?
Yes, sir, I have.
See, this is your T2G or EG. This is your T2G and this is your EG. See the situation. You have already done this up to this part. Now you have the 6th electron, so it will go in this. So that's why T2G4. Now for the 7th electron, you can see T2G is already fully filled. Now it will go. The next electron will go in EZ. Now this will be T2G5. After this, it will go in this and then easy. Are you getting my point?
Yes, I am.
Can you do the rest?
Okay, sir. Yes, sir. Done.
Very good. Now we are going to do the splitting for. You are done with this. Just match your answer. Okay. For 8th electron, it will be T2G6 easy. For 9th electron, it will be T2G6 because it is already fully filled. For 10th electron, it will be T2G6 easy. But here you can see it will go T2G6 easy 2. Then it will go T2G6 easy 3. Then it will go T2G6 easy. Are you getting my point?
Yes, sir.
Now you are going to write for a spectrochemical series, which one is more strong, which one is less strong, that one weak field or a strong field ligand. So here it is a spectrochemical series. Spectrochemical series. So write with me. This is the lowest, weakest, Br minus, I minus, then Br minus. Then comes your SCN minus, then comes your Cl minus, then comes your S minus 2. Then comes F minus, then comes OH minus, hydroxide. Then comes your C2O4 minus 2. After this, NCS minus. And after this, EDTA4 minus. After this, NH3. Then En, then Cn minus, then Co. This is the spectrochemical series in which you can see this is the strongest one. These are all considered as the strongest. Okay, strong. Yes or no? Got it?
Yes, sir.
So please do write it. Then
Yes, sir. Done.
very good. Now see the splitting for tetrahedral we are going to see. So d orbital is splitting. In a tetrahedral crystal. tetrahedral crystal field. So here is your d orbital. One, two, three, four. So d orbitals, free I. You can write like this. And after this, we'll go up to this. And then again, this one. Wait a minute, please. Can you see the screen?
Yes, sir, now I can see.
So this is 1, 2, 3, 4 again. Now this will be divided into two parts, split it into two parts. This and this. Only the difference is that you can see the upper level is now reversed in this. Wait a minute, please. Now see, it will be 3 and here it will be 2. And for tetrahedral, we call it E and this is T21. And this is EO. Again, the barycenter, what we call it, barycenter. And this difference is basically 2 by 5 delta T. Delta T is basically CFSE, that means crystal field stabilization energy for tetrahedral, of tetrahedral. Are you getting my point? T is for tetrahedral.
Yes.
And this energy gap is basically 3 by 5 delta T. So this is how the splitting in tetrahedral takes place. Please do write. Let me know when you are done with this.
Yes, sir, done.
Very good. Now the next topic is basically your bonding in metal car. Do you are you giving the mock test on Friday?
No, sir.
Why?
So because I'm studying for my other school tests. That this is aim time. So
Okay. So it is bonding in metal carbonyls. So first of all, it should be homolactic. It is shown by only basically carbonyls present. As a ligand, only carbonyls are present. Only carbonyls are present. And since only one type of ligand is present, that's why it is homolactic complex. What it is? It is homolactic complex. As for example, I'm going to write some of the example. Please do write with me. Like NiCO4, you have seen this. NiCO whole 4, and it is tetrahedral. Tetrahedral. Then comes your Fe, CO, then CO. This is your FeCO whole 5. Since it has 5 ligands, coordination number 5, so it is trigonal bipyramid. Trigonal bipyramid. Then comes your chromium CO, that is carbonyl. This is also CO. Carbonyl, this is also CO. Carbonyl, this is also CO. This is also CO. Carbonyl, this is also CO. And it has a formula like this. And since it has coordination number 6, so it is octahedral. Please do write up to this, then let me. Are you done with this? Aman, are you done with this?
Yes, sir. Hello.
Okay. Yes. Aman, are you there?
Yes, sir. Sorry, my mic is
Please,
lagging.
no problem. Please do write this, two more example of this. This is also carbonyl compounds. This is cobalt, which is connected with cobalt. This is C double bond O. And this is also C double bond O. And this is cobalt. This is cobalt. This is cobalt. And we can write the formula CO2, CO whole 5. Wait a minute. It is CO whole 8 it will be.